Thank you very much, Dario. First of all, let me thank the organizers of this seminar for inviting me. So I've been asked to give some wide audience talk about this equation that Dario already mentioned. But just to tell you a little part of the story, I'm going to talk about PDE, an evolution PDE, which is integrable. Integrable means, okay, there are plenty of definitions, and it's not so easy to define very precisely what's an integrable PDE. But let's say it's a PDE for which you can compute almost explicitly the solutions. Okay. Now, this equation, Benjamin-Ono equation, was introduced in the end of the 60s, first by Benjamin, who is an expert in fluid mechanics. So it's really an equation that you can meet in fluid mechanics. I will tell you why. And it turns out that this equation attracted many people, most in physics first and then in mathematics, because it has this integrability property, but it's also, even among the known integrable equations, it has quite surprising properties. And these are the properties I would like to talk about today. So, most of the work I'm going to present here was obtained in collaboration with Thomas Kappeler, who sadly passed away almost a year ago now, and Peter Topalov. And this concerns this Benjamin-Ono equation. So again, the birth date of Benjamin-Ono equation is 1967, and you can find easily the paper in Journal of Fluid Mechanics. The paper by Benjamin. So Ono is a theoretical physicist from Japan who studied this equation and gave more information about this equation a little further. This is in 1975. Okay, so what is it about? So it's about a two-layer fluid with an interface. Okay, and so we are interested in gravity waves, and we will be interested in the regime of long gravity waves, long waves with gravity. So here you have typically some air, and here some water. And you look at the interface between these two fluids, and for every x here, you look at the displacement that will, at time t, theta of tx. Okay. Now, there are several models for this, and in particular, what makes the difference between these models is the depth of the water. For instance, if the depth of the water is very small, then you will find an equation which is probably the first one which was derived, which is the Korteweg-de Vries equation. In fact, derived by Boussinesq, but okay. And now, if you look at finite depth, not small, not big, you have something rather complicated, which is called intermediate long wave equation. And if the depth is going to infinity, then you get the Benjamin-Ono equation. So what does it look like? The Benjamin-Ono equation reads as follows. So zeta, again, is a function of time and position, one-dimensional position. Okay. And it looks like this. dt zeta equals, let me put some constants for the moment, which is not usual for mathematicians. So we have some constant nu here, and another constant, let me call it 1 over tau dx of d square, zeta square. So zeta is like a length, okay? It's a displacement. So nu will be like some length to the square divided by time, and tau will be like a time, okay? For the moment, okay? What is mod dx? Mod dx is the Fourier multiplier. So if you look at Fourier transform from hat, and you look at a function f of the x variable, so the Fourier transform of mod dx f for a wave vector k is just by definition absolute value of k, Fourier transform of k. So you should not be surprised by this operator, which is a pseudo-differential operator, because essentially we are working in the regime of water waves. So you will have to, because of you are dealing with irrotational and incompressible fluids, so at some time you will have to solve the Laplace operator in typically an upper half plane. And if you solve the Laplace operator in the upper half plane, and you look at what's going on the boundary, you will have the Dirichlet to Neumann operator, which relates, so the first initial boundary and to the second initial boundary value. And this Dirichlet to Neumann operator is precisely this one. So this guy is in fact very natural when you are dealing with fluid mechanics, as soon as you have infinite depth. Okay. So now, what can we say about this equation? First of all, once I've written these two parameters, I can say that, okay, I can forget them. In fact, I can forget them just by scaling. Okay, so if I write zeta with appropriate constant lambda, alpha, and omega, I can find lambda, alpha, and omega such that the function u, the new function u, will satisfy the same equation with nu equals 1 and tau equals 1. Okay, so that's a very easy exercise. I still write t and x, my variables. Well, they are not exactly the same, but whatever. I get that, right? And in fact, I have even more flexibility because I have 3 parameters. I just need to kill 2 coefficients. So I will use the third parameter in order to fix the periodicity in x. So I will assume that I'm working with periodic boundary conditions in x variable, which means that I will assume that zeta satisfies something of that kind. And if I choose correctly my 3 parameters here, I can assume that u is 2 pi periodic, moreover, just by taking omega equals 2 pi over L, of course. Right. So that's that's a very natural thing. So this is the first observation I wanted to make. It's a very natural one. The second one is that there is another transformation that you can make on this equation. So I will rather work with this one. But of course, in the physics literature, you will rather see the other one. So the second point is that there is a first conservation law, which is a very natural one, which is the average of U. The average of U is conserved, well, just average both sides of the equation. You will see here you have derivatives. So when you average, this cancels. So this precisely tells you that the derivative with respect to time of the average is 0. Okay? Now, this average is in fact at your disposal. Why? Because if U is a solution of the above equation, and if A is any real number, then I can prove that the function A plus U of t x minus 2at is still a solution. So of course, the average of this guy will be A plus the average of U. So since A is at my disposal, I can always assume that A equals the average of U equals 0, for instance, just by withdrawing the average of U. Okay? So these are my first reduction. So I will now deal with the function U, which is 2 pi periodic, and with average 0. Okay? If I need it. Okay? Now, what are people interested in when looking at this equation? Well, you can see it immediately in the paper by Benjamin. In fact, the reason why Benjamin got really interested in this equation is that he found, and this is even in the title of his paper, he found a solitary wave which is quite explicit. So, the second part of my talk is about what I call special solutions. And the most interesting, maybe, special solutions are solitary waves, which are solutions of that kind. U of tx is just U0 of x minus ct. Solitons, if you prefer. If you know a little bit about the Korteweg-de Vries equation, you know that this equation became really famous because of that, and because of the observations that were made in Edinburgh about this channel and this soliton, which was traveling. And this soliton, in the case of the Korteweg-de Vries equation, is a Sech function. Here, it's something much simpler. It's an algebraic function, algebraic. If I was on the line, really, with assumption 0 at infinity, it would be an algebraic function. Here, it's a very simple object. It's a Poisson kernel. 1 minus r squared, 1 minus 2r cosine x, plus r squared, where r is a parameter between 0 and 1. I claim that if I start from this initial datum, this one has average 1, but okay, you can withdraw again its average if you prefer. Then I claim that the solution of the Benjamin-Ono equation with this initial datum is given by that. And that was the observation by Benjamin. With a constant c here, it's a velocity c, which depends on r. Okay? And in fact, you may ask whether there are other such special solutions, and it was proved 25 years after this, by Amick and Toland, 24 years, it was proved that they are essentially the same, the only one. So, essentially, the only solitary waves. It's not exactly true. You should add also functions of the kind n, u0 of nx, where n is an integer, okay, a positive integer. Clearly, it will be also a solitary wave. But the theorem by Amick and Toland tells you, if you look for a solution of that kind, periodic in time, in x, periodic in x, it has to be of that kind. Okay, so that's a nice result. Now, Ono was also aware of this solution, special solution, and this Japanese physicist said, okay, what about interacting these two kind of solitary waves? What happens if I start from the sum, for instance, of two such guys with different R, etc. And, well, he started to make calculations. And in fact, again, several years after this, people realized that there are plenty of other solutions which have a very nice property. So if you start now from initial datum, which is a sum, of finite sum of such solitary waves. And let me say that, moreover, I will, for every term, I will introduce some phase shift here, alpha j. What happens? Well, the fact is, and that was proved by people like Matsuno and Birkhoff, so Japanese school and Russian school, Birkhoff and Krishever, around the 90s, I think. They proved that the solution will be of the same kind for all time, except that, of course, Rj depends on time, and alpha j depends on time. And the Rj and alpha j will satisfy an ODE system. And it turns out that this ODE system is integrable in the sense of Hamiltonian systems. It's integrable in the sense of Liouville, Kovalevskaya. So you can write this system. Maybe a little more complicated, but you can write it, you can do it. I mean, if you plug this expression in the Benjamin-Ono equation, it's a long computation, but you will have a system. So this is what we call a multi-soliton equation, solution. There are plenty of multi-soliton solutions. So if you know a little bit about integrable PDEs, you say, okay, if you have such property of multi-solitons, exact multi-solitons, this means that there is some integrability of the whole equation. And that's indeed the case. That's indeed the case. So we will see a little bit more why it is the case, but for this I have to look at more general solutions. So more general solutions will arrive if I look at typically what we mathematicians call global well-posenness. Of the initial value problem. The Cauchy problem. Okay? So imagine I'm given a function u0, which is 2 pi periodic, Let me assume it's smooth. Of course, all of my functions are supposed to be real valued, okay? And it's important. So it's real valued. Now I claim that there exists a unique function u of time and x, which is smooth and real valued. It's 2 pi periodic in x, again, same periodic boundary condition, which is solution of my equation of BO, Benjamin-Ono, with u of 0 x equals u0 of x, which means. So this theorem was proved, in fact, by Jean-Claude Sau in 1979. I give you an initial value, an initial interface. It tells you that there exists a smooth, initial and smooth interface. There always exists a global solution. So, of course, for physicists, it might not be so surprising. But for mathematicians, it means that we can, in fact, control some information about the solution for a long time. And in particular, one can prove something more surprising. Namely that all the derivatives, furthermore, all the derivatives, so if I take any integer, okay, all the derivatives of my solution, and I take the supremum on x on 0 to pi, say, of this, are bounded uniformly with the time. So you cannot expect some transition to high frequencies. If I start from a smooth datum, for all time, uniformly in time, all the derivative will be bounded. This is another expression of integrability. It tells you that there are, in fact, many conservation laws. Many conservation laws for this equation, which control high regularity, which control these guys. And that was, in fact, observed by people like Brock and Krushkov and Nakamura, essentially at the same time, just before Sau proved his theorem. Okay. So again, coming back to finite dimensional Hamiltonian system, when will you say that a finite dimensional Hamiltonian system is integrable in the sense of Liouville? Well, you have some Poisson structure or symplectic structure, whatever, and you will say, okay, I'm a manifold of dimension 2n, and I need to find n conservation laws which are independent and in involution. They are commuting in the sense of the Poisson structure. Of course, as n goes to infinity, it's not so clear, because the fact that you have infinitely many conservation laws, well, is this infinite enough? Is not so clear, okay? But at least this is already a very remarkable property that there are so many conservation laws so that you can control all the regularity of your solution. Now, in fact, you can make this property more precise, and well, I'm going to introduce a little more mathematical analysis. I'm going to talk about Sobolev spaces. So to go a little further than this, I need to introduce Sobolev spaces of periodic functions. So given a real number S, I will define HS of t, and I will put some subscript here. R means that I will look at real valued function, and 0 will be that I have average 0. Okay? So these are functions f, which are from t to r, functions or distributions, so that if you look at the average of f is 0, and you demand that the Fourier coefficients satisfy that the following series is convergent. So you look at all the wave numbers here. They are integers because I have 2 pi periodic function. And you demand that this guy is finite. So what does that mean? It means in some sense that the s derivative of your function f is square integrable. For instance, s equals 0. Well, h0 is just the L2 functions, okay? Square integrable. If s is bigger, then you will have, for instance, s equals 1, you will have f square integrable, and the derivative of f square integrable, so it's more regular. But on the other hand, if s is negative, well, if s is negative, you might not have a function, but rather a distribution, okay? Whatever. Now, I claim that, why do I introduce this guy? Because we proved with Thomas Kappeler and Topalov, Peter Topalov, something like 3 years ago, that the flow map, if you look at the flow map ST, which sends smooth functions, 2 pi periodic, real valued, and average 0 to the same, and which sends the value at t equals 0 to the value at t of your solution. So you look at the theorem by so. You give me an initial datum, and I give you the value at time t. So this is the flow map. This can be continuously extended as a map from HS to HS, not for all S, of course, but for all S strictly bigger than -1/2. -1/2 corresponds essentially to the regularity of the Dirac mass, -1/2 minus epsilon, okay? The Dirac mass is in h -1/2 minus epsilon for all epsilon positive. So this is absolutely unauthorized. You cannot solve this equation with the Dirac mass. But you can solve for HS for S bigger than -1/2. Okay, if you remember the equation, I'm sorry, I've erased the equation. I can write it down again. The equation looks like this. dtu equals dx mod dxu. Well, this is nice because this is linear. Minus ds of x u squared. Well, if u is in L2, u squared makes sense. It's in L1, it's a function. If u is a distribution, Laurent Schwartz told us that the multiplication of distribution in general is impossible. And this starts with HS for S negative. But still, even if this formulation of this equation does not make sense anymore for S negative, the flow map still makes sense. So you can still talk about weak solution in some sense of this equation. Okay? And this is perfectly well defined. There is only a unique way of extend this. Moreover, it's not only that you can extend it. You can talk about the long time behavior of your solution, so as t goes to infinity. Moreover, the function the trajectory u, which stands t to st of u0 for every u0 in hs, r0, and s bigger than minus a half. This function, so it's a function from the line to some Hilbert space. It has the following property that it is almost periodic. Almost periodic, what does that mean? It's a definition that was introduced by Harald Bohr. Harald Bohr was the brother of Niels Bohr. Okay, so and Harald Bohr said that almost periodicity is something very nice. It tells you that for every small epsilon, I can find a length such that every time interval of length L, so L may be big if epsilon is small, of length L, contains something that we call a pseudo period, some tau, such that for every t in R, u of t plus tau minus u of t in the space Hs, so the norm here, this is the square of the norm, okay? In the space Hs is smaller than epsilon. So what does that mean? It means that essentially you can approximate this. In fact, this is a nice result by Bohr. You can approximate such functions by finite sums of what you call generalized trigonometric polynomial. You take a vector v in Hs, you multiply by e to the I omega t, where omega is a real number. This is, of course, periodic. Now, if you take a finite sum of such things, it's no more periodic. It's quasi-periodic. Now, if you look at the uniform closure of this, you get these functions, almost periodic solutions. And I claim that every solution of the Benjamin-Ono equation, whatever the regularity, Hs, okay, is almost periodic in Hs. It tells you in particular that there is some kind of Poincaré recurrence. It tells you that as t goes to infinity, you will find a sequence Tn goes to infinity such that u at time Tn will be very, very close to the value at time 0, for instance. This is included in that. So it tells you something about the dynamics. Okay. So, yes. So what is there behind that? What is there is what I will call a nonlinear Fourier transform. When you are given a PDE with constant coefficients, you can, well, we know that, we can apply the Fourier transform and transform this equation is something much easier. For instance, if you look at the evolution PDE with constant coefficient, you can apply the Fourier transform in the x variables and you get just an ODE on Fourier coefficients. So I claim that there are such guys also for this equation, but of course the Fourier transform is not the same. It's a nonlinear one. And sometimes we decided rather to call it a Birkhoff map. So the Birkhoff map for BO is a map of that kind. So it sends this space Hs to a space of sequences of complex numbers, exactly as the Fourier coefficients. Okay, so I look at the space that I will call Hs plus a half. So what is this? It's the space of Xiens for n at least 1, such that sum of n 1 plus 2s Xn squared is finite for n equals 1 to infinity. So essentially, a little bit like Fourier coefficients of an hs plus a half function. Now I claim that there is a map of that kind which sends any function u in hs to a sequence Cn of u, and this is nice. It's one-to-one, it's bijective, it's even a diffeomorphism. If you know a little bit of symplectic geometry, it's in fact a symplectomorphism, it's symplectic. It has many nice properties, such that the evolution of the Benjamin-Ono equation is completely trivialized by this, in the sense that if you solve the Benjamin-Ono equation, any solution, I look at what I will call the generalized Fourier coefficient of u at time t. This is Cn generalized Fourier coefficient of u at time 0 times what? Times something which is rather simple, e to the it omega n of u at time 0. And omega n is completely explicit in terms of the Cn's. Omega n of u0 will be n squared minus sum from k equals 1 to infinity, there is 2 here, minimum of kn ck of u0 squared. Okay, for those who know a little bit about Hamiltonian systems, we have found objects which are called action angle variables. The Cn are complex numbers. You should think of square root of the action e to the I, the angle. And here, these guys, omega n, they are called usually the frequencies. They tell you that if you think of the solution as a trajectory, this trajectory is in fact up to applying this map, is just a line which is unrolling on a torus, maybe possibly infinite dimensional because there are many ends, with a constant angular velocity, which is this guy. This is the angular velocity for every end. So you have a torus of infinite dimension. The Cn, observe, the modulus of Cn is preserved, clearly, because this is real. So this has modulus 1. And the velocity here has a very nice expression. So the ck of u0 squared, they are what people would call actions. And you have a nice relationship between these actions and the frequencies. And this is one of the very few examples of PDEs for which this relationship between actions and frequencies is so simple. For instance, try for KdV. For KdV, it's much more complicated. It's not even explicit. You know it exists, of course, but it's not even explicit. Here it's extremely explicit and extremely simple. Okay, so this is, of course, construction of such a Birkhoff map, of course, requires a lot of work. But the idea behind this is that there exists some lax pair structure. Some lax pair structure. So the key is lax pair structure, because precisely it's called that way because the first lax pair which was introduced by Peter Lax for the KdV equation. So essentially, a lax pair is that you are on some auxiliary Hilbert space, and you have a pair of two operators on H, such that which depend on your state, u. So u is my state. Typically here, these are functions which are 2π periodic and real valued and average 0, say. And such that if u is a solution of my evolution, of the evolution equation, then you have the following property that dt of Lu equals the commutator of Bu with Lu. So this is very useful. In general, this guy is self-adjoint. Not always, but here it will be the case. And this one is anti-self-adjoint. As a consequence, by a standard ODE argument, you will see that Lu at time t is in fact conjugated by a unitary operator to Lu at time 0. And what is really nice is that, of course, it means that the spectrum of Lu is a conservation law. In our case, in fact, the spectrum of Lu is a discrete spectrum. It's made of eigenvalues which go to plus infinity. And so it tells you that all the eigenvalues are conservation laws. Moreover, what is really nice is that, for instance, I can give you the relationship between Xn of U and the eigenvalues lambda n of U. In fact, you can prove that these eigenvalues have the very remarkable property that the difference between two consecutive eigenvalues is at least 1. And so the relationship is that the action guy here, the square of Xn of U that you see everywhere, is in fact this guy. Well, it's one of the properties. Okay, so the other interesting property is the connection with special solutions I introduced. Connection to multisoliton. The connection to multisoliton is that U is a multisoliton if and only if this is finite gap, in the sense that the set of n such that Cn of U is different from 0 is finite. In some sense, multisolitons, which are very specific things, correspond to sequences of Xn's which are 0 starting for n big enough. Okay, so just in the remaining time, I would like to give you, sorry, I'm probably already out of my time, but to give you an application of this to doubly periodic solutions. So again, just for simplicity, I'm going to work with solutions which are 2π periodic with average 0. And now I claim, does there exist such solutions which are moreover periodic in time? So U of t plus capital T x equals U of tx. Does there exist? Well, you will tell me, of course. For instance, solitary waves are periodic in time. U0 of x minus ct, okay, it's periodic of period 2π over c, okay? But multisolitons, they might be. Well, it's not so clear. I mean, in general, they are not. But if you fit correctly the parameters, you can find them. Okay. Are there others? That's a very good question. Are there other periodic, doubly periodic solutions which are other than multisolitons? And the answer is quite striking, in fact. The answer is the following theorem. If t over 2π, so t is my period in time, 2π is my period in x, is rational, and if U is at least L2, so it has at least square integrable regularity in X, then U is a multisoliton. So if you demand a little bit of regularity, again, square integrable in X, and if you impose that the quotient of the period in time in the period in X, 2 pi here, is rational, then there are no other periodic. Now, if you take T over 2 pi irrational, there are others, which are, for instance, L2, but not H1. And you can also relax, not the irrationality. So you take, for instance, T equal 2 pi. So in that case, of course, every L2 solution is a multisoliton. But I claim that there exist other solutions to doubly periodic, which are not in L2, but which are HS for every S negative. So in some sense, and this is maybe the most intriguing result, it tells you that even in the case of 2 pi, so you just take doubly periodic in 2 pi in time and in X with the same period. If the solution is L2, nothing else than multisolitons. Now, if I allow my solution to be slightly less regular, HS for every S negative, then I can find many others. So it's quite an interesting question to know whether such solution can be seen and can be detected. I don't know at all. But at least the theory gives you the existence of such things. And of course, I don't have time to give you the proof, but the proof uses essentially this and the nice properties of these omega n functions. Okay. So just as a conclusion now, I would like to ask, do you know any other integrable PDE for which you can prove this? KdV, nonlinear Schrödinger, any other derivative nonlinear Schrödinger. There are many for which we know that there are some lax pairs, etc. For the moment, the answer is no. And I asked Thomas Kappeler, who is also quite an expert, about KdV with periodic boundary condition, and he told me no, I cannot do this for KdV. So in some sense, I can conclude my talk by some provocative statement that Benjamin-Ono is more integrable than KdV. Thank you very much for your attention. Thank you very much. Other questions?
Can you give an explicit expression for the lax operator?
Yes, of course. It was found by several authors, but in particular Ablovics and Focas introduced that in the beginning of the 80s. So first of all, the auxiliary space is not L2, it's the Hardy space on the torus, which means that you look at Fourier series which are L2, but with only non-negative Fourier modes. So this is a usual Parseval condition, but you just look at only non-negative Fourier modes. Okay? And then you have an operator, which I denote by pi, which is, so let me call it L2 plus. You have an operator which is the orthogonal projection from L2 to L2 plus, which consists, you take a Fourier series, and you forget all the negative Fourier modes. Okay? So you just cut the Fourier series. So, and then my LU operator is just the following. 1 over I ddx, the standard one, which is a non-negative operator here because its eigenvalues are n, for n from 0 to infinity, minus, so if I pick a function f, minus pi of UF. Just this. This is what is called a Toeplitz operator. Toeplitz operator. Yes, because the multiplication by U does not send this operator, this space into itself, because it introduced negative Fourier mode. So you just project it, and you get this nice pseudo-differential operator, Toeplitz operator. This is for BU, for LU, and for BU, this is I T mod du minus TU square. TU square, which is TU times TU. Okay. So it's a nice, I mean, if U is sufficiently smooth, it's a nice anti-self-adjoint and bounded operator. And you can see that if U is a solution to Benjamin-Ono, then you have ddt of LU equals BU commutator LU.
In the case of the KDV, the operator B is related to a fractional power of the Lax operator.
No, yes, in the case of KDV, the Lax operator is Schrödinger. Schrödinger minus d square dx square plus u. And BU, I think, is you have terms in dx cube. So maybe, yes, you can take 3/2 power of that, yes. But here it's a differential operator. Both are differential operators. What is nice here, different, is that you don't have differential operators. You have Toeplitz operators. So it's another world of non-local operators, and this makes the analysis more delicate, but also, finally, more explicit in a way that I cannot really explain. I mean, we found out finally that. So the existence, the fact that we are in the Hardy space, introduced some more rigidity. Thank you. More questions?
Just a curiosity, whether in this theorem by, I don't know.
So, Jean-Claude So.
You write down the Poisson kernel for the problem? You solve the Doubly problem?
No, it was no. The Poisson kernel is not explicit at all for the nonlinear. No. It's too complicated. No, what it did is he solved the problem for small time by an iterative scheme, and then he proved that the crucial norm, which is H2 norm, cannot blow up because of conservation laws that were found by other people. So in some sense, he proved the existence, but he didn't have to have any kind of representation of the solution. In particular, it was very difficult for him to have this almost periodicity property. So you really need integrability to prove that.
So thank you very much.
Thank you.